an outbreak of cholera in Soho, which was the original Soho, which was a district in London. Back then, the London sewage system hadn't yet been extended to that part of the city, and people were getting their water directly from a well, and lots of people were getting sick. A physician named John Snow decided to go around, interview all the households, gather data on who was getting sick, and where they were collecting their water. He used some fundamental statistics and very quickly discovered all of the people getting sick were getting water from one well. Snow convinced the city to break the handle off that well, and most of the diseases went away. So one of the earliest applications of learning in statistics, although it's not machine learning yet. Here's a heat map of the same thing. You can see the red area where most of the disease was concentrated was directly from that well. So, machine learning, which is a core piece of artificial intelligence. It's really understanding how you make a decision under uncertainty. Because if you know exactly the correct answer, you don't need software, you don't need to learn anything. And decisions under uncertainty involve statistics and it involves probability. In general, and this is a gross generalization, there's two types of machine learning. There's regression and there's classification. We're going to take a look at both of those. Regression is looking at something where you need a number. How tall will the next person who walks through that door be? What's the average amount of dollars the visitor to my website will spend? How many minutes do I have to wait for my Uber? It's late. Classification is more often what you see in a lot of the newer, trendier things, and that's, does something fall into a group or not, as a yes or no decision. A classic example in medicine, will the patient die? If you're Google and you're looking at photos, is this a picture of a cat? Yes or no? And so on. So you have regression and classification. Sometimes the problem can be looked at both ways. If we're looking at the stock market for a hedge fund, you could do regression. What will the price of the stock be tomorrow? Or you can do classification. What's the probability the stock will close up tomorrow? So part of doing machine learning is understanding what you're trying to look at. Now, in statistics and machine learning, we like to look at things backwards. No machine learning algorithm on the planet ever is always correct. If someone tells you it is, they're lying. So the goal is to be less wrong. And it's an expression a professor of mine used years ago, and I always liked that. You're going to be wrong, but how do you be the least wrong possible? We do that by defining what we call a loss function. What is our loss? It can be money, it can be the health of a patient or the number of years a patient will live. It can be time, it can be customer satisfaction. But how can we minimize how wrong we are in predicting that? If we think 90% of our customers will be satisfied with a recommendation and 20% are satisfied, that's not a very good algorithm. So let's start looking at this. And remember, no math, I promise you. This is a very simple, what we call a regression graph. What we're modeling or showing here is that y depends on x somehow. Doesn't matter what y and x are, again, no math. But you can see all the dots, and you can see, okay, there's generally a trend. As x goes up, y goes up. You can plug this into Microsoft Excel or software or any system can do it, and you'll get that nice red line. And that red line is formally called, there's an acronym, BLUE, Best Linear Unbiased Estimator. And basically that means that's the best line you can estimate given that data. But notice something, that line doesn't touch a lot of the points. It's wrong for most of those points. If I come to you and say, hey, I have a new thing with the x of 40, what's the y going to be? You're going to get it wrong. But it's the best you can do with the data. It's the least wrong model. So this is how we look at it. Each point, if you see the vertical line, is to measure how wrong that point is. And you would add them up, and ideally we add up the square of the line so that we get rid of the signs. But you have something called a mean squared error, mean absolute error, and you minimize that with the best line. But that's ultimately what machine learning for regression is doing, is finding the best line that minimizes the error. Now, maybe you have two predictors, so you can think of this sort of a 3D plot. You have x1 and x2, and y is the vertical. And when you get into the world of mathematics, it doesn't matter how many predictors you have. You can have 1,000 dimensions. Of course, you can't draw it, but you can have as many as you want, and you're still trying to find the best line through them. You can get into the non-linear models where the line curves and twists and change shapes. Again, it's just mathematics, but the concept is the same. Now, that takes us to the next case. If we're doing classification, There's no why. The why is either yes or no. The patient lived or died. It's a cat photo or it's not. So why tends to be 0 or 1. Well, that causes a problem because you wind up with a graph like this where you say, okay, the lower values of X, Y didn't happen, and the higher values of X, Y did happen, but there's some overlap. So there's something called a logit. And again, no mathematics in this talk, I just want you to have the concept. This curved S-shaped line is the logit. What that represents is the probability that Y is 1 given X is the input. And again, you can do this across multiple dimensions and linear and nonlinear curve and all the other fun things. But the concept is the same. You're never saying Y is true. You're saying this is the probability Y will happen given the input. And I know this sounds like a simple concept, but these are the fundamental building blocks that most machine learning algorithms build on. So the general workflow is you have some sensor to collect data. That can be pulling tweets off the Twitter feed. It can be looking at the historical prices of stock. It can be some new high-def infrared fancy camera. It can be 16 microphones around a room capturing speech. It's a sensor. The next challenge is feature extraction. Okay, I have all these pictures that my high-def camera took. Well, what's the input? What are the X's to this model as we're looking at? How do we decide what those are? And that's where a lot of the interesting work gets done. And then at the end of it, once you have your features, you build your classifier. You try to make your probabilities as most accurate as possible. This is an example of a feature extraction called the Moore feature extractor. And quickly, computers see things as numbers. So a pixel on the screen, I'm sure you've all heard about megapixels in your phone and cameras. A pixel is a dot, and that's represented as a number between 0 and 255. If it's a color picture, you have red, green, and blue, and they each get a number between 0 and 255. That's it. So this is an example of black and white, or maybe it's just the red channel or something. And what they've done is they've rotated the sensor through 360 degrees and looked at the stripes it makes, and that now gives you a bunch of numerical features you can input into your classification algorithm. It's messy, it's complicated. This was, until a few years ago, state of the art. Now, how we learn once we've extracted our features, and this is a very rough diagram of something called supervised learning. You take some information where you already know the answer. You call it a training set. You look at the history of stock prices, you look at the history of experiments on a patient with a medicine, history of horses running a race, whatever it is, and you teach the system. Let's input some training data, let the system come up with a model. Well, it's wrong, there's an error. Okay, let's use that error to make our model a little better. And we'll output again and make the model a little better, and so on and so on in a big loop. Well, at some point, your error gets smaller, 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 it gets as small as you can get. And you say, okay, for this type of model, for the data my sensor had, for the feature extraction I designed, that's as good as this model gets. That is, I've minimized my loss function. Now, if it's not good enough, you can go back to the drawing board and come up with new ways to sense, new feature extraction, adjustments to your model, and so on. But supervised learning is how all this machine learning works. And your hope is that if it learned to model the training data very well, when you give it some new test case that hasn't seen before, it will also model it well. Now, this is an example of a classification system with two features. There's X1 on one axis and X2 on the other. Here, the Y's in a sense are blue and red. So you can think of blue, picture of a cat, picture of a dog, patient lives, patient dies. And notice something, the circle points are the errors. This is the best line or the best classifier this process could get, and it's still not perfect. There's always some loss. You can extend it and look at 3 classes, or where the more advanced work is being done now is you get something like this. And this is modeling, it's a classic problem, modeling flowers. Don't worry about what it means. And what you're treating is everything is now a probability. You're not saying this is a photo of a cat. You're saying, well, there's a probability it's a photo of a cat, but there's also a probability it's a photo of a dog. There's some overlap. And this is how you can think of it in a computer. If you have a world with cats, dogs, and bears, there's only 3 things your picture can be. The probabilities have to sum to 1. That's a law of nature. So on the left, it's most likely a photo of a cat. In the middle, it's most likely a photo of a dog. And on the right, yeah, the bear is stronger, but not that much stronger than the dog photo. Maybe there's some similarities. So another part of machine learning is what you do with it. How do you, the end user doesn't want to see this. How do you present this? Do you just pick the highest probability all the time? Do you give them a choice? Do you show both photos? So interpretation of your machine learning is where the human element comes into play and the user experience and the user interface comes into play. Now, one of the next evolutions is something called a perceptron. It was developed in 1957 by a researcher named Rosenblatt. There was a lot of work on studying how do humans think and how do humans learn. And in your brain, there's something called a neuron, which is a single, I guess it's a type of cell. And they theorized the neuron has input from other neurons from your body, and it either fires an electrical signal to the next neuron or not. So Rosenblatt decided to represent this in a formula. So you have all the inputs coming in from whatever in your machine learning. There's some formula in the middle, often that S-shaped curve, that logit that we talked about before. It's also called a signal. And then there's an output. Now, where that's useful is if you stack them together, a bunch of neurons, you get what's called a neural net. Neural nets were originally developed, I believe, in the early 60s. They had a resurgence in the 1980s, and they're coming back again now because they're a nice way to learn. One of the next evolutions, which I'm sure you've all heard of, is deep learning. A researcher named Jeffrey Hinton looked at neural nets and realized instead of a neuron firing yes or no back here, well, what if every neuron had a probability? And it had a probability of firing. The probabilities influenced other probabilities and influenced other probabilities and on and on and on. And came up with some new math on how to fit that. And this is currently what's state of the art. It's what Google did when it won the Go match. It's what the new self-driving cars are using for recognizing pedestrians. This is it. Now, the other advantage of this is they're not doing feature extraction. Instead of figuring out, is this an eye, is this a mouth, is this a face, they just throw all the raw pixels into it because you have thousands of these inputs and tens of thousands of layers, and the software finds the features and learns the features on its own. So it's really starting to show some interesting intelligence. But remember, at the end of this, underneath all that output, there's still a classifier. The self-driving car looks and says there's an 82% probability that's a stop sign. So it's still doing that classification between 0 and 1. It's just doing it in a much, much smarter way. And this is an example why you want probabilities. One of these is not a cat. But you have a probabilistic model, it's the one on the left. Maybe, there's a small probability that's a dog. So, do you say they're all cats? Well, that's probably the least wrong answer. But again, interpretation. Now, another thing along the lines of interpretation is, what do you do with it? Once you have your output from some model that gives you a number, so what? So what a lot of systems do internally is something called expected value. If you have, in this case, your function is money, it could be time, it could be quality of life for a patient, it could be anything. Given the probabilities, what happens financially to each possible choice through every possible path that the world can take? If I think that's a stop sign, an 82% chance, and I stop, what's the outcome? If I think it's a stop sign and I don't stop, what's the outcome? If I'm wrong about it being a stop sign and I stop, what's the outcome? And so on. And you can find the choice that has the best expected value for the end user in their domain, what they're trying to do. And it's an important part of understanding machine learning because now you can make a decision. You say, based on all the probabilities and based on all the things that we think can happen next, this is the best choice. Now, to wrap up, there's really, in my mind, 4 ways you can innovate. And since this is a room of entrepreneurs, to give you some food for thought. There's always room to innovate in sensing. How do you gather that data? Where do you gather that data? In this example we saw earlier, you're looking at students' test exams. I don't think anyone's ever looked at that before. Interesting data source. Feature extraction. What are the features? Are you pulling out semantic meaning, like we just saw? Are you using deep learning, where you're just looking at raw pixels? Do you want to invent some new sound processing algorithm to break up the sound wave? Lots of interesting work to do with feature extraction. Then there's classification and learning algorithms. A lot of the fundamental algorithms have been worked out years ago and they work well, but now we have big data. And the problem with data is if you have more data than fits in the RAM of your machine, or more data than you can add up, you have a problem. So there's a lot of interesting work you can do on how do we modify these learning algorithms to work with billions of data points, but what if the data is streaming in, like Facebook posts, faster than you can process it? So there's lots of room you can do in there. And the last category is decision making. What do you do with it all? If you have some model that tells you it's a photo of a cat or the car thinks it's a stop sign, how do you represent that to the user? How do you process that in a way that's useful and deliver a working product? And again, lots of ways to look at reporting and interpretation. So 4 ideas for you to think about. I am based in Hong Kong, and I operate a consulting company called Data Science Services, so I'll be around after the talk if anybody has questions. Thank you.